Hey guys, and welcome to my 2211 lab number 2. We're going over the change in position over time, predictions versus observations. So as introduction, this lab has the purpose of capturing the motion of the projectile and modeling how it would behave both when gravity is the only force acting on the object and when drag is also allowed to influence the system. So it highlights the fact that which forces one models and to what degree of precision has a tangible impact on the final position of the object, and that increasing the number of forces accounted for in a simulation generally improves its accuracy. So the main idea is the motion of a projectile in the force update equation. So as projectile moves, the force of gravity and drag are both acting on it, altering its velocity over time. The force of gravity is always acting in the negative y-hat direction, and the force of drag is modeled by this equation, which uses the square of the velocity and the drag constant, and it is always going in the negative velocity direction. So because drag is not constant, this force must be iterated each frame and used to update the object's velocity using the velocity update formula. And this updated velocity can then be used to model the final position of the projectile after a certain length of time. So what we found was that the model that took into account both gravity and drag aligned the closest to the real trajectory, and while the model which only accounted for gravity was a decent estimation, it overshot the trajectory of the ball due to a lack of a decelerating drag force. So our procedure was we filmed the motion of the ball as it was thrown and landed on the ground. We then used Tracker to track the position of the ball frame by frame over time, and then using the initial position and velocity identified by a tracker, we created a model analyzing only the force of gravity, and then another which analyzed the force of gravity and drag. And then finally, we compared the observed trajectory of the ball to the two models by graphing them. So this is the motion that we were tracking. And as you can see in this image here, the x-axis goes to the right, the y-axis goes up. The system is the paper ball, the surroundings are the atmosphere, the Earth, the entire universe. The force of drag is going directly downwards, velocity is in the motion of movement, and drag is opposite of the velocity. So modeling trajectory with the force of gravity and drag, to find the initial velocity, we took the first two measurements from the tracker video, and using the equation for the average velocity over a very small interval, we can approximate both the x and y components of the initial velocity vector using these calculations here. We can then put these into our GlowScript code by declaring the mass of the ball, the position and velocity, the acceleration of gravity, which is always 9.8, and the drag force, proportionality constant, which was determined experimentally. And to establish the net force, we use the equation seen here, where the force of drag is the only force acting on the x-axis, and then both drag and gravity are acting on the y-axis. We then updated the velocity in an iteration, and used the updated velocity each time to update the position in the same iteration. So the model that only factored in gravity, in order to do this, we simply set the drag constant equal to 0. This removes the influence of drag from net force, and only gravity will be factored into the model. So comparing the results, we can see that the gravity plus drag trajectory is the closest to the observed trajectory in terms of its arc, and that in all three cases, the projectile is still accelerating downward. So some sources of error could be the inconsistent measurement of the ball's center of mass by a tracker, as that can change the initial velocity, and difficulties in modeling drag. Of course, it is hard to simplify drag into a single constant, and it is likely that constant is not a perfect estimation of its true level of drag. So did the projectile reach terminal velocity? In all three graphs, including the one in which drag was simulated, the projectile continues to accelerate in the negative y and x directions by the end of the time interval. Its terminal velocity is when the projectile is falling at a constant velocity, which indicates a net force of 0. The magnitude of the force of gravity would equal that of drag, which is not the case in any of our models due to the evident acceleration. And to make an experiment which tests the terminal velocity, you would have to allow the ball to fall from a significantly further height, such that velocity could induce enough drag to counteract the force of gravity and establish a net zero force. And then what if the ball was thrown straight up with the same initial speed? Would it take the same amount of time to reach the ground? So with the same initial speed, throwing the ball directly upward would take more time to reach the ground because the vertical velocity is larger. So for example, consider two balls thrown at a speed of 5 meters per second. One's going directly vertical and the other at a 45-degree angle. So ball A is traveling upward at 5 meters per second, while ball B, you have to use trig, and you find its initial vertical velocity is only 3.54 meters per second. So by using the velocity update formula, solving for the time it takes to reach the peak of the trajectory, as seen here, and then multiplying that length by 2, we are assuming a symmetrical trajectory here. You see the time it takes for a projectile to reach the ground is entirely dependent on its initial upward velocity, and therefore ball B, which was thrown at an angle and thus had less initial vertical velocity, would take less time to return to the ground than the ball thrown directly upward with the same speed. Thank you.